This lesson is going to be on implicit derivatives, which is really just an extension of chain rule. Before we start with that, we have to really go back and do some review and recall some notation and learn some terminology. Remember that when I write dy dx, that's our symbol for derivative, but that literally means the derivative of y with respect to x. And we've been abbreviating that as y prime. But when I have like y equals, let's say 4x squared plus 3. Okay. The reason I write dy dx is that y is written in terms of x. You can see that we've got y, and over here is the x variable. So when I write dy dx, or just y prime, okay, technically this is really what I'm doing. And you can see how this applies with the chain rule. I'm going to bring down, using the constant multiple rule, the derivative, or the 4. Then I take the derivative of, let's think of that as something squared. So the derivative of something squared is 2, something to the first, times the derivative of the inside, which is really dx dx, the derivative of x with respect to x, because we're taking our derivative with respect to x. Plus, then we already know the derivative of a constant is just 0. So we've been writing it before as just dy dx is 8x, because dx over dx is really just 1. So we've not been using this notation of dx over dx, but that's going to get to be really important today, because we're going to be working with some derivatives that we imply, or that we define implicitly, meaning that we don't isolate the y variable by itself. So maybe it's too difficult to get it separated, or it's going to make it really nasty if we do. Let's kind of look at some more notation for a minute. Say we had that S is 4 pi r squared. Okay, that's the formula for the surface area of a sphere, and it's based on the radius. If I were going to take the derivative, I would want to find ds dr, because S is defined in terms of r. All right, so ds dr would be 4 pi as a constant times the derivative of r squared, which is 2r, and again, let's think of this as something squared, so that would be 2 something to the first, times the derivative of the something, but that would be dr dr, which again, if you divide something by itself, that's going to give you 1. So we don't normally put this part, because we have the function defined in terms of r. So we're going to have ds dr would just be 8 pi r. Okay, so that's the way we've been doing it, again, without adding that notation of the dr over dr. All right, so let's look at some problems where we're going to actually be doing some implicit derivatives. Okay? So we're not going to isolate the y. And again, we look at that because it could be that it's just really difficult to do that, or if we do isolate the y, it makes our equations really nasty. Here would be an example of that. Okay, that's a fairly simple equation, but if I were to get the y by itself, then what's going to happen is I'm actually going to end up with 2 equations, because I would subtract x squared from both sides and then take the square root. And when I take the square root, remember, we get a positive solution and a negative solution. That also is going to involve that I'm going to have square roots in the problem. Those are a little uglier to take derivatives of. So what we do is we just leave it in the form that it's in, and we just start taking our derivative. Now we're going to find the derivative with respect to x. All right, so the derivative of x squared with respect to x, since it's the same variable as the one we're taking it with respect to, we just do our normal derivative. The derivative of x squared would be 2x plus. Now here's where it gets a little weird. Okay, you got y squared, but we're taking the derivative with respect to x. So this is going to be a kind of a chain rule problem. So what's the derivative of something squared? It would be 2 something, so it's 2y, times the derivative of the something. So the derivative of what's inside parentheses, well, that's the derivative of y. We write that as dy dx. Then we go to equals. That's our next thing. And then the derivative of 12 is 0. Now the idea is I want to get dy dx by itself. So at this point I'm going to start solving this equation for just dy dx. So I subtracted 2x, and I get 2y dy dx, okay, this is still multiplication here, equals negative 2x. Again, remember, we're trying to get the dy dx by itself. So then what I'm going to do is I'm going to divide both sides by 2y. So dy dx is going to equal, well, this 2 and 2 is going to cancel, so I just get negative x over y. And that's your answer. All right, now you got to look back and kind of make sense of this. The fact that our derivative started with x's and y's allows us, and we didn't isolate the y by itself, allows us to leave our answer with x's and y's. Now there are a few times where you could actually replace that y value and find out what the derivative would be just in terms of x. This is not one of them. You'd want to do that. We probably will not even see one where we want to do that. A lot of times if you're doing the second derivative implicitly, you do that. Okay, let's look at another one. How about 4x cubed minus 5y squared plus 3xy equals 15. So we start by, we're going to take the derivative of this. So I want to do d dx. The derivative of 12x cubed would, or I'm sorry, 4x cubed would be 12x squared minus, then the derivative of 5y squared would be 10y dy dx. Again, remember, the 2 is going to multiply with the 5 to give me 10. Y to the first times the derivative of the something, which would be the dy dx, plus, then to take the derivative of 3xy, I have to do this as a product rule, because you're multiplying two things together, a 3x and a y. So let's let u be 3x and let v be y. So we'll just come off to the side here. Say if u is 3x and v is y, then u prime is 3 and v prime is dy dx. It's the derivative of y. Then we do our Jesus fish, and you're going to have 3x dy dx plus, and then the other diagonal would be 3y. Now those two things together, put that in green, those two things together are the derivative of the 3xy part. And then we still have to take the derivative of 15, which is 0. Now in this case, this is a little different than our previous example. If you look back at our previous example, we just had one dy dx. Here we've got two. So here's what we're going to do. We're going to keep everything that's got a dy dx on the same side and move everything else that doesn't have dy dx to the opposite side of the equation. So I'm going to subtract off a 12x squared and a 3y. And that'll keep just these dy dx's. So that'll keep this term and this term. So when I do that, those are going to cancel. You're going to get negative 10y dy dx plus 3x dy dx equals, and then on the opposite side I have negative 12x squared minus 3y. Now it doesn't matter what order you put that side in. You could have negative 3y minus 12x squared. Now, there actually is kind of a process to this. Once you get all the dy dx's on one side and everything else to the other, your next step is to always factor out the dy dx because they have that in common. So we're going to factor out a dy dx. When I do that, I get a negative 10y plus 3x. The other side we're just going to leave alone. Now, to get dy dx by itself, I divide both sides by negative 10y plus 3x. Now, you're going to see some really nasty looking answers. So dy dx would be negative 12x squared minus 3y over negative 10y plus 3x. Now, I do want to point out something. Here's one place where we sometimes run into some trouble with the multiple choice part of the test. Because I kept my dy dx's over on the left-hand side of the equation, I could have moved dy dx's to the right-hand side of the equation, and what happens then is the signs are all reversed. So you don't know when you're looking at the problems and they're multiple choice which way that the solution will have had the dy dx's moved. You don't know if they'll move them to the left or move them to the right. So you kind of have to look at the possible solutions. Had I moved everything up on opposite sides, what would happen would be all the signs would be reversed. So instead of having negative 12x squared minus 3y, I'd have positive 12x squared plus 3y. And then on the bottom, I would have a positive 10y and a minus 3x. Okay, so you have to watch for both of those possible solutions when you're solving these. Okay, let's look at one more and throw in a trig function. How about we've got 3y squared plus 5x equals the cosine of y. All right, so we start taking our derivative. The derivative of 3y squared would be 6y dy dx plus the derivative of 5x would just be 5 equals the derivative of cosine of y is negative sine of y times dy dx. Notice that every time we take the derivative of something that involves a y, you've got a dy dx added on. Okay? So we're going to move everything to that has a dy dx to the same side, keep everything that doesn't on the opposite side. So I'm going to go ahead and just subtract a 6y dy dx. And when I do, that's going to leave me with just a 5. Those are going to cancel. I can get 5 equals negative sine of y dy dx minus 6y dy dx. Now once you get all the dy dx's together, we factor that out. So we're going to factor out a dy dx. Still got 5 equals. And then we'll have negative sine of y minus 6y. Then to get dy dx by itself, we divide by negative sine of y minus 6y. Now again, you've got several possible solutions to this. So I could have what we said, 5 over negative sine of y minus 6y. You also could change the signs of everything and make it negative 5 over positive sine of y plus 6y. And then the other thing they might do is actually just put the negative in the front of the entire fraction and put negative and then 5 over sine of y plus 6y. Alright, and that's really all there is to implicit derivatives. Again, it's just kind of an extension of the chain rule. You're going to find after we work through these for a couple days that these are actually one of the problems that the kids like the most. It may not seem like it now, but they actually do really well with these. By the end of the year, it's one of the few derivatives that we don't have to spend a lot of time reviewing. They just remember those. So hopefully, after a few days of practice, we'll be good at these.